Welcome everyone to the Israel Institute for Advanced Studies in Jerusalem. We're very happy to welcome you here today. First and foremost, because it is the first Midrasha after COVID started. So it's after 3 years of no activity. We are happy to have you here and relaunch the Midrasha. We're going to have 2 of them this year, isn't it? Yes, we're going to have 2. So the Institute was founded in 1975 as a safe haven for scholars who come here for longer periods, for 5 to 10 months. But apart from our research program, we have 6 advanced schools for PhD students, and the Midrasha is one of them. And we are very happy with that. Apart from greeting you, I can't say anything about your topic. I'm an historian, a medievalist. So I couldn't even figure out what the title of your Midrasha is, but I'm sure you all know what it is about. And I wish you a fruitful and enjoyable meeting around you. So thank you and welcome to the Institute. Thanks. Thank you for holding that. So we're going to start with the first of our 3 tutorials, and this will be called Scanlon tutorial on O-minimality. Thank you. Thanks, Kobe. So I do actually plan to take historical approach to the subject, but history only goes back to the future. Plus, maybe that's part of that. I'm also going to be taking, I hope it's a rather elementary approach. And
you have better suggestions to how to move the slides forward.
So it should.
Right, so there are a number of canonical sources in the subject. That's many of you may have already looked at, and I recommend sources that should continue reading. The book by Van den Dries on canonical was published in 1986. Is really intended as an introduction to O-minimality for use by people who may or may not be interested in the aspects of the logic. To some extent, he's de-emphasized its origins in logic, which can be useful, and also miss some things. I'm going to be actually repeating some of the material from this book, not much. Okay, so in the first lecture and a half, my intention is to talk about basic O-minimality, the topics that's what's being known about O-minimality in the 1980s, early 1990s. And you can find many more details in that book. The material on counting theorem, so the applications to algebra, that's the purpose of this feature talk, not covered. It's not covered in this book. Really, there is no good section of counting. The other, say, canonical reference, and I say canonical because these according to Mathematicae, this you see it's like 350 countries. There's written some odd citations, which for math use, as a they really take the point of view that O-minimality should be thought of in the same light as synthetic analysis. And they've done everything they can to hide logic. I mean, it's logical. It's intelligent the way that's written. But there are no Christian forms in this paper. I only talk about the points. So if you don't like them, sorry, I'm going to be very silent, but talk about the points. But this really is it's a fantastic reference for the geometric theory. These days understood in the 90s. Okay, so by the mid-90s. What's somewhat interesting about this paper is that it was, in some sense, the writing of it was inspired by Hodgson. Say in some sense because there's no Hodgson directly in this paper. But Wilfried Schmidt became somewhat aware of the possibility that O-minimality might give you contain this phenomenon, which we used to understand functions which are not analytic, but to be a little bit beyond. And the kind which, as we now have learned, do appear in calculations of Hodge theory, and asked, to what extent does this theory actually apply? And they wrote this paper in order to answer that question. Although it's not directly addressed in the government paper. Those are two sources that I'd recommend if you want to go back and study this in more detail yourself. There's no way in 3 hours. The basics. So for me, the theory really starts in making theory. With the work of Karsti on real fortunes. So you might say 1930, you can point out to the date when the publication is 1951. There was a war between the time that he worked on this and got around to actually publish it. So the work took place around the same time that Gödel's work on undecidability, completeness, and number theory. When Karski was most interested in the decidability aspect of this, that's elementary geometry. And we thought of in the way that Euclid would have thought of which the geometry was decided. Which is fantastic. That's not for us what's the most relevant part of what he did. For us, what's the most relevant part is that he really described what the definable test looked like in the real field. What's the algebraic geometry? How's the algebraic geometry is? And that's really where O-minimality comes from. And so I'm just going to tell you, this is again very classical. Classical meaning that's not 11:30. So it's very classical work in the model theory of model fields. And that is it's understanding what the axioms for the real numbers are as an ordered field. So what's you can do, and there's more than one way to present this, but I want to use the presentation where we have the ordering because it's going to match the way that we think about forming the O-minimality. Since you can write down a countable list of axioms which describe all of the first order properties of the real numbers. That's what we do. And I think I've a little bit. This first one I just says, you know what these are. Okay, so basically there's the multiple. So to write down the axioms, you write down the axioms that you know from basic algebra as to what an ordered field is. So you need to say that issues is associated with data. You need to say that multiplication should be shown. You need to say that addition and multiplication gave you all respective ordering. And so, for example, if you multiply by a positive number, numbers less negative, it's all the same inequality. And so on. Okay, so you know what those axioms are. And if you don't, you can figure them out. And so the basic axioms for what's in order to deal with. That, of course, doesn't pin down real numbers because the rational numbers satisfy those axioms, but they give you an order to deal. And so there are two axioms which you add to say basically that the ordering is complete, even though you can't really say that. So what you'd like to say is you'd like to say that the real numbers are the unique complete ordered field. But that's not scriptural logic. So in order to say that the field is complete, you need to quantify over all sequences. So these are all kinds of. And that requires second order quantification. you want to see this, what can you see in the elementary theory? You have these two consequences of completeness. And so one is that being a square is the same as being positive. And the second, which actually come to be, well, these are not always independent, but the second one that I'm going to give is the sign change property. So polynomials are continuous functions. And they're continuous function of the real numbers. It takes at one point the negative value, another point the positive value, somewhere between the basket shots. But you can just write that down algebraically. Write down algebraically the condition that's for each polynomial of each degree, you have to change the sign, it has a difference. And that's it. That's all you have to say. So Tarski's theorem is that the axioms that just wrote down give you complete axiomatization of the real numbers as an order field. But he's most interested in
real algebraic numbers, the real closed field.
yes, yeah. So the real algebraic numbers are also a real closed field, and they satisfy these axioms, even though they're not complete. I mean, they're not complete as a topological space, but it's complete in the sense that every first order sentence which you can express as language, just through the real numbers we through the algebraic numbers, and vice versa. Yes, the real algebraic numbers are an example. Another model of this, another model of this theory. We satisfy these axioms. So satisfy the same consequences. For Tarski, the most important consequence is the second one, that this theory is decidable, meaning that there's an algorithm which takes any first order sentence about the real numbers and answers correctly whether it's true or false. For us, in looking ahead to O-minimality, just last week, just to work on it eliminates quantifiers. You know, so a little bit more, a little more about what that means. And so, how does it prove this? So I'll say a little bit about what goes into this proof. Say that the key technical ingredients is an old algorithm of Sturm from 1830. So it's 100 years before Tarski worked with this, which allows you to count how many zeros a real polynomial has. It takes an interval, and you have to compute sign changes involving the function, its derivatives, and its higher derivatives. You have to take various remainders. There was an algorithm which may have that before. But you can compute some finite level number of steps of computation, gives you a certain number of sign changes, and you can use that to determine how many zeros you have of your polynomial between any two numbers. What you have to show in order to show that these axioms are complete is that you really don't need to work with the real numbers in order to get that algorithm to work. That is a consequence of the axioms that so you have to show formally you can use that algorithm if we're computing a number of zeros from a polynomial by just immediately by a formal consequence of those axioms. Can somebody say a little more about what's really involved? So we're trying to prove quantifier elimination. What quantifier elimination means that you show that any formulas, any expression that you might write in the logic found structure with variables. And so my variables here, you don't look like variables if they frankly most of the constants, A1 to AN. You want to know whether you can determine whether that formula is true, even though it involves asking whether something might exist or it happens for everything. So there might be a huge number of alternations to quantifiers here in the formula we're interested in. You want to know whether you can determine that just by asking whether certain polynomials applied to these numbers, A1 to AN, are positive or negative. That is, whether there are quantifier-free conditions. Now, there's a general procedure, general inductive procedure, where you can check that if you can solve the problem where you eliminate one existential quantifier, then you can always solve it. Because how do you build up formulas? You build up formulas by applying Boolean operations and one existential quantifier. And if you can get rid of that step once, then you can always get rid of it. Okay, then it'll be, you'll never have to go through that inductive step of adding these into quantifiers. So it's a somewhat simpler situation you have to deal with. Now, to be completely honest, there should be more complicated Boolean operations here and everything. But again, just general Boolean algebra nonsense and produce the products. So we have to decide: is there some number? Well, I should say number, but it's really something in this real close field. Is there something in this real close field which makes this finite list of semi-algebraic conditions hold or not? Now, relative to x, this is just one variable polynomial. Very basically, we're asking whether for this finite list of one variable polynomials with coefficients that are functions of the AIs, can you find something which makes it always positive? And so, well, now you can start to see where Sturm's algorithm can come into the picture. Okay, so you show that you can break it, you can break this up, and you can find some rational functions which basically give you more or less the boundaries between the zeros of these various functions. So you have to compute those, compute wherever those go, and of course there are some cases you have to worry about denominators and the actual algorithm is more complicated than we're going to write here in one paragraph. But you find those rational functions, and now you can arrange that for each one of these, the sign of the polynomial when you plug in the x is constant in between. So now you can just check. You just go through and you evaluate the sign conditions on each of those points, and it gives you now it's like a semi-algebraic condition on the AIs to determine can I make polynomial 1 and polynomial 2 both positive at the same time. Well, that's going to be true if there's one of these finite intervals that's listed out where one of them works, and then becomes quantified as a condition. That's the basic principle. It says actually unwind it requires work which I told you where to read it. Okay, so go back and Tarski's paper. Talking to Jordan yesterday about this, so that's he couldn't get through Tarski's paper. I don't know why. It's a really beautiful paper. It's really nicely written. It's long, but part of the reason why it's long is because he tells people what personal performance. It was written. Like he worked this on 1930, people didn't really never thought about how to connect logic to algebra. So he takes the trouble of explaining. Okay, so it's explained. It's explained in detail.
Do you think the resolvent of like two polynomials or something?
Yeah, I mean that's the kind of thing that's involved.
Yeah. Because otherwise you can't really get. You don't really know what the two are.
Well, yeah, of course. So so here it says, okay, that's still hot. So you start with this, you do some work, you first replace the FIs to make sure that they are square free, so you don't have anything additional for have some repeated roots, and that doesn't change the sign for this one. And then you also, like if the resolvents, you want to know if they can have some common roots or not, so you have to work out where those are, each of these things. And then you have to work out for two of them at a time, what's happened to the third one. So it's so there's what's written here is not enough to complete the computation, but interesting the kind of thing you actually have to do to complete the computation. And like I said, Tarski's paper is really nicely written. It's it's a little bit dated, but it's nicely written. It's a good place to read how this approach works. There's a more modern approach when we talk about in a moment, which you might prefer. I'll find out. Okay, so what quantified elimination says from geometric language is that the definable sets, that is the sets or the solution sets to formulas, are semi-algebraic sets. And a semi-algebraic set is just a set which is defined by the positivity, where I'm all zero, the positivity of a polynomial, and then take all the polynomial. So that's just literally the quantified elimination sets. So that the semi-algebraic sets are exactly the sets that you can define. using first one. There a little slide here, which is sub R here, which I'll point out, which means that you can allow parameters. And so you can plug in numbers into the formulas and definitions, and then that would be normal sets. If you don't allow yourself to plug in numbers, then you only get semi-algebraic sets that are defined in brackets. And this has this consequence, which we now call O-minimality, that the sets definable in one variable are just finding using points and intervals. Why is that? Well, one of the basic sets, there's one variable polynomial, so f of a1 greater than equals 0. What does that look like? All right, so it looks like the zeros of f. And finally, any of those, unless f is the zero polynomial, in which case it's the whole line. And finally, zeros. And then some of the intervals between the zeros. Okay, so it's two successive zeros. Either the function is always positive or it's always negative. It's always positive, you get that whole interval thrown in here, and it's always negative, it's out. And the finite Boolean combination of sets that look like that, all sets that form. Finite Boolean combination of sets which looks like finite unit points intervals is itself finite unit points intervals. So the semi-algebraic sets in one variable, just that. It's the definable sets relative to the theory of real closed fields are just finite units of points intervals. That's what we call O-minimality. This property is the characteristic property. Now the isolation of that as a property reappears in this paper of Vandenbries from 1982, which you see he says that it's remarks on Tarski's problem concerning r plus times and x. And this problem, which is as he's raising, it's raised in that earlier paper, and it's that paper on decidability of the real field. I'll tell you a little bit about what this problem is in a moment. In this paper, Vandenbries does not use the word O-minimal, but he uses the idea. And so he calls the condition I just wrote down, that every definable subset of the lines on the intervals having finite type. And finite type is pretty much an overused term, so we're not going to use that. O-minimal is another word. Okay, so what is this problem? It's Tarski's problem. So Tarski asked whether you can decide the real numbers with the exponential function. And he was a little vague as to which exponential function, but he kind of like x goes to 2 to the x. Yeah, which is nice. And so that's a good exponential function. We don't know the answer. The closest to a positive answer we have is this 1996 theorem of McIntyre and Wilkie, where they showed that if Shannon conjectures, and you only need it for the real numbers, and in fact, you don't even need spikes in this wrong form, you can get into it mixed form. But if Shannon conjecture is true, and what does Shannon conjecture in this in the real case say? You take real numbers that are limited independent of the rationals, alpha 1 to alpha n, limited independent of the rationals, and then you also look at the exponentials, and here I've given you the exponentials in the power. The transcendence degree of the field that generates, alpha 1 to alpha n, e to the alpha 1 with the e to the alpha n, has to be at least 10. You know, it's reasonable. I don't know how to prove it. And there are people in this room who know how to prove functional versions of this. But this one, maybe there are people in this room who know how to prove this too, but they haven't told me that they know how to do it. So this is hard, right? But if it's true, then that theory is decided. And of course, they do it actually with the theory with e to the x, our favorite Euler's constant, but that's not a big deal. Because you can go between e to the x and 2 to the x, by the differential equation that satisfies. So in the first structure, the second, the 2 to the x is definable, and vice versa. Okay, so you decide the first thing you decide. The Tarski's question has a positive answer if this rather difficult number theory hypothesis.
These main implication on the other side, you can get some.
Yeah, that's a good question, and yeah, it's a good question. So I mean, what what they can show is that somehow you can yeah, so that's a good question. It's open. Like, I don't want to say there is something that you said, but it's technical. I mean, say it wrong. I'm not excited about the words.
I have to add question.
What's that?
No, is there, I have a how question that question. Is there an O-minimal theory that's like known not to be undecidable? Or known not to be decidable?
Well,
is there any
you
relation
can
between
Okay, so because if you just throw in a function that's is not recursive or something, it's just
But how do you know that the thing that you get?
oh well okay, so one thing I'm going to explain is you can get any restricted element function. So an element function, real element function defined on the closed interval. And you put that in as well. And you can arrange that that's not recursive.
Yeah, okay.
So yeah, so that's the geometry doesn't actually say anything about active values of the functions.
Yeah.
Can you replace your two by any other number?
Yes. Yeah, so you can replace it by any, not even any real algebra. And it's so basically the reason is that once you have once you say you have one exponential function, say you have 2x, you also have log base 2. And so you have raising to powers with any number that you can any other number, basically. And so you can break down the differential equation that satisfies the function satisfied by the equation. So yeah, so you can move between in this structure or that structure, all of the exponent, but a whole slew of other exponent functions.
So the transcendentality of the number e is not.
It's not so important. Yeah, if you can replace it with anything which is definable in the exponential definable equation. Those things that are definable, those numbers that are definable in structure. You can replace different values through the base. And so there are a lot of kinds of
So for Shannon conjecture, it also doesn't matter if we're taking E or powers.
the two. Now there it does matter because for instance, if you were to put here 1, the 1 is linearly independent from it's not 0. Okay, so it's and Q adjoint 1 and 2 has transcendence degree 0. Okay. And but we wanted to have 1, but it would have 1 if we put a B. So it does matter for the statement. The decidability parts, no, but the statement directions indeed this.
One other small comment. I think that for the understandability, you don't even need analytic functions. You can just take R alge. If you add a sufficiently generic constant, it will already be undecidable.
That's good point. Yeah. Well, maybe we can do R alge. Do R alge adjoin sufficiently generic. Constant. Yeah. So it'd be so would it be the real algebraic numbers? It'd be the real algebraic closure of Q of T. That where T is some sufficient field, where you put it into the reals. Okay. All right. So how does this question motivates what Vanity was doing? So in this paper, so he knows various things. There are various other things I just thought I'd point out because again, you should go read this paper. It's a beautiful paper. But there are lots of things. I'm pointing out the reason I'm pointing the paper out to you is because these are worth reading. This one is definitely worth reading. He shows, for instance, that you cannot prove quantum validation for this one. It'd be impossible. And basically because you can do some kind of blow up construction that's just there's no way you could possibly describe certain projections by quantum. Can't prove quantum validation, but he speculates about a way you might prove some level of quantifier simplification. Model completeness would be good enough. And he shows how really you can just use the differential equations. So don't really think so much about the theory, but think about the differential equations. And he was right. This actually is a good way to go about well, he didn't prove it in this case. And he notes that, well, if this worked, then that structure would be O-minimal. We didn't actually call the O-minimal. And then you can start doing something else like geometry for that structure. But he said, well, why don't we just do that? Okay, so most of the paper is about doing the basics of O-minimality in the hopes that you can apply it to the exponential function. And he was right, we can apply the exponential function, but we'll find that I can know that. So, where does this come from? It comes from this work of Collins in computer science, published in 1975. I think he said that's the actual for this 1972, where he gave an alternative proof of Tarski's quantum combination theorem by developing what he calls cylindrical algebraic decomposition. And we usually just worry about the cell part of it. I'll say cylindrical part is going to usually project image. Every time you project it's still a nice decomposition. Now, what he did, he showed that when you take semi-algebraic sets, you can break up the whole space in such a way that they fall into these nice cells. And we're going to define what cells are in a second. And then you can use those cells in pretty much the way that I was discussing through Tarski's argument to decide existential questions. So he does the cell decomposition, starting with the quantum prior predefinable sets, and then using that to show that actually that's it. Like you don't have to worry about quantum primes. What Vanderjus does is he takes the consequence of quantum prime elimination that you have a dual minimal, that you just have points and intervals in one variable, to show that you can do this decomposition. And then once you have that decomposition, then all the definable sets become really nice. And it's really easy to understand. So let me tell you what the cells are in the cell decomposition. Okay, so it works in any structure where we have hidden order. And in practice, in most cases, you're going to think about the case where that structure is the real numbers, with the usual order of the real numbers. But there can be good reasons to generalize, to not just talk about this. Now we have to decide what's the set. Okay, so if you want to be a logician, you start to 0, and you say that the cell is just 1. But nobody likes that. So we're going to start with 1. Okay. So we're going to start with 1, and the cells are points or intervals. And intervals are intervals. B should be less than C. I allow negative infinity or plus infinity to be one of these guys. And it's everything we think. So no interval. You can those 2 points. It is important in some applications of underlying more complicated kind of structure here with real numbers, that the endpoints really need to belong to R. So you can't say do a cell decomposition of the rationals by taking irrational numbers. And then you go to higher dimensions. So there are 2 kinds of cells in higher dimensions. One kind of cell would be the graph of the continuous function on the lower dimensional cell. So I have an interval, and then we have a continuous function on it, and then we get graph. That's a cell. Or you can have parameterized intervals. So you have a cell in the lower dimensional space, and you have 2 continuous functions on it, and you arrange that the first one is always smaller than the second one, then you can take the space in between. Those are the cells. And all right, I also allow that the interval might fall with infinity or the positive infinity, but I think you can like get those conditions. So those are the cells. And the cell decomposition theorem says that definable sets be broken up into definable sets. So more precisely, well, I'm sorry, let me give this statement of the definition and then the theorem. So structure is O-minimal if it's totally ordered by the specified order relation. And in one variable, all that you can define are points and intervals. We're defining using points and intervals. That's what it means to be O-minimal. And it's strongly O-minimal if that's a property of its theorem. And if you don't like that, in a moment, you don't have to worry. But so technically what this means is that I take any other structure which satisfies the same first order theory. It's the first thing, and there's this dot, dot, dot. There's lots of other structures that might have it. Take somebody else's set that's exactly the same first order theory. It's also a minimal. So the definable sets one variable there, points in this. And what can go wrong is you might have, it might be that in your given structure, you can define, say, in some uniform way, you can find a set which is 5 points, and another one is 10 points, another one is 500 points, and it goes off to infinity. Then when you go to an ultra product or some elementary extension, you could plug in some parameter, and you can define a set that's infinite, but it's discrete. That doesn't actually have an interval.
So, what here means the structure formula, the language?
As by structure, I mean it's a first order structure in a language, which includes the order relation and more symbols, which I'm not writing down the actual symbols are. Or maybe the actual symbols could be empty, those are also allowed. But it's a first order structure in language that has at least a binary relation symbol and possibly more, probably more symbols. And relative to that language, every definable subset using parameters in one variable is a finite human function.
So I didn't understand, there could be two different orders in the
Sure.
structure.
If you want, we have three orders. Okay, turns out that they can't, but if you want, sure, that could be, the language could have two orders. Although there's one distinguished one and then another one which is, you wanted to be perverse, you added the second one, that's fine, you can add the second one if you like. There's a symbol for second order. And then it would have to be the case that even using a second,
So a real closed field must be relative to this distinguished order.
well, that's a theorem, I guess. Yeah, so it's an O-minimal real close field. Would have to be with respect to that's the usual distinguished order that makes it into a given order. Of course, there are structures, you can put orders, and that's fine, that's allowed as far as what a structure is, but it probably won't be O-minimal. Because the second order relation, if you have an interval with respect to the second order relation, that has to be something you can express as a finite unit points and interval with respect to the first order relation. Now there are some you could do. For instance, you can take my second order relation could be the reverse of the first order relation. Okay, that's fine. I'd allow that. Okay, that would still be O-minimal. But if you do something at all interesting with the second order relation, it's not good. Okay, so Andrew's theorem is that if you take a strongly O-minimal expansion of the real numbers, then you have solid decomposition. And so solid decomposition means that if you take finitely many definable subsets in some Cartesian power real numbers, for instance, semi-algebraic sets in R(n), then you can partition the whole space into finitely many cells, so that those cells also partition these cells. Notice here, his hypothesis here is strongly O-minimal, which means you have to say something about the whole first order theory. And he's also doing it on the reals.
But to make practical use of this theorem, you need some means to check whether the structure is strong or minimal, which is
Yes, it's just hard. Okay, so yes, that's hard. And okay, so maybe I'll jump ahead just a second. So I'll tell you not to worry, because shortly after Vanderjuice did this, there was some work by Steinhorn and Pillai and Knight, where they showed that you don't need to assume strongly, and you also don't need to assume those the real numbers. So you would only need to check in that one structure that the definable sets in one variable or points to this, which in principle could be something easier to do than actually working out the whole possible theory of this. All right, so well, so before I keep going, how long am I supposed to talk? And I can see a clock, so let me am I supposed to end at 10 to? Or is it?
The one page 7 and 5 are
Okay, great. Okay, so let me explain to you, let's sketch out how this proof is done. And I'm actually going to give, not quite like every last detail, but pretty close. And the hypotheses that Van der Waals has, it's much easier to prove self-decomposition than it is in hypotheses without strong O-minimality and without being this. So that's part of the reason why I like these hypotheses. It makes it possible to do it without working quite so hard. But it's good that some people worked hard to eliminate those hypotheses. But just to understand what's going on, let's go through and look how it works and the strong hypothesis. So there are two basic lemmas you have to prove about definable functions. First, you prove that every definable function is continuous. Well, that's not true because I mean, piecewise continuous. So it's continuous except finite points. You have a definable function from the reals to the reals. That's all the finite points is continuous, which is nice. And so actually one thing that's maybe I should have said this before. I often think about O-minimality as being the context where what you do in your calculus classes works. Okay, so when you teach calculus, you pretend like every function is going to draw. You pretend like you can tell whether it's increasing or decreasing or the derivatives. And okay, maybe there are a few finite points for us defining cases, but no, that's it. Yeah, that's what O-minimality is. Okay, so that's what it looks like when we'll stuff. You think that you integrate into two variables, you can always break it up in finite pieces for you can really do that. That's what self-decomposition, for instance. So you can always do that. And of course, it would be start doing more real analysis kinds of things, it doesn't work. But O-minimality, first or calculus works. It's how much. Okay, so let me show you how to prove this. And it's really just like very basic real analysis. Okay, so O-minimality, okay, one beautiful thing about O-minimality says that if the world isn't as beautiful as you think it should be, then it's horrible. So if it's not, if this function is not continuous almost everywhere, then there'll be an interval where it's discontinuous everywhere. So you go to that interval, and you can find one point for continuous, then you won. Okay, that's all you have to do. So this function, if it's false, you find an interval where it's discontinuous everywhere. You know, yeah, sure, those functions exist, but not in O-minimal way. All right, now you look at each subinterval, and better not be constant with an interval. If it's constant, well, then it's continuous, right? So it's not constant. So the image would then have to be infinite. Right?
Why
So
should be constant?
but it won't be. It won't be. I'm saying it can't be. If it's constant on a subinterval, it's continuous. And we know that this function is discontinuous everywhere. Right? We're going by this contradiction to say, yeah, this function it doesn't satisfy the theorem. The points where it's continuous is a definable set, but it's discontinuous is a definable set. So if it's false, the whole interval where it's discontinuous. And so on that interval where it's discontinuous, it can't be constant on any subinterval. The word's continuous on that subinterval. Good. So it's not constant on any subinterval. And in fact, it has to have an infinite image on any subinterval. For exactly the same reason. For finite, every subinterval where it's constant. So take a subinterval, the image has to be infinite. Always. Okay. Now what we're going to do is we're going to build sequences like we do in the first year analysis class, where it's going to shrink. We're going to find the A of the BNs, so that when you get the function on the A and the BN interval, it's going to land inside of some interval that has a length of most one of them. And make these guys. Okay, so how do we find those?
Thomas, excuse me my stupidity, but the set of rational numbers is not O-minimal, right?
As what? Which structure?
The okay, with the natural order and natural field operation.
It's not. Yeah, it's not O-minimal in that one.
But why?
Why? Because you can define the squares. So the set of
Okay.
squares is definable, and it's
so
not a finding in.
If we stand by taking algebraic, real algebraic numbers,
The real algebraic numbers are minimal. And you have to use charge consider. So you know, the definable sets, one variable are given by positivity sets, one variable polynomials.
so what if we define the like in the Dirichlet function, which is 0, it's irrational numbers, and 1 algebraic rational number.
That is not a minimal. And it's not a minimal because you can define the rationals. And that's the rationals will be definable. And they're not finding in the point intervals. So they don't contain any interval inside of this.
Fine, so somehow we can't define this Dirichlet function in this structure.
That's right.
Of addition and multiplication.
Yeah, right. So that's a consequence. Yeah, so consequence is that it's in the theory of real closed fields. In the structure of the real algebraic numbers, your Dirichlet function is not defined.
Can't even define the integers.
You cannot define integers, so integers are horrible. Okay, so okay, well, actually,
But God created.
a lot of things, right? A lot of things.
No,
Was it Gauss or?
I think it's Gauss, but I'm not sure.
No, the integers are they talk a lot of problems. Although tomorrow I'm going to talk to you about how the integers are good. So how even though it's like a category confusion, you can actually say something about integers using O-minimality, which it's still is wrong, but it's quite relevant. Okay, so let's actually talk through what it's about. Okay, so we're doing this little real analysis thing. Right, so the images of our interval is infinite. So it has to contain an interval. Right? So this contains an interval is small interval, like most one. Right? Because an interval is shrinking. One. The image that's small interval is also definable, is also infinite. Remember, our function is not constant in any part. So it contains a small interval, like this one. And let's just take the closed interval inside of there. That's where A1 B. Good. And I'll just keep going. So you do the same thing with make the length 1/(n+1). And if you look at the limits, get AN's going to converge to somebody on the reals. This again where the reals helps. So it has a limit. And functions continuous there. I just arrange it so it's going to be continuous at that point. But it's supposed to be discontinuous everywhere. And so the function has to be continuous. The conclusion is a function was actually continuous almost everywhere. Doesn't happen. I'm not using trigonometry. This is just O-minimality on the reals.
So what is so special about continuity? Can't you prove the same way that function is differentiable?
Yes. Yes. So it's also, yeah, so yeah, in fact, the next, maybe I won't go through the steps of the I've heard of the whole proof here, but I won't talk through this one. So you can show that's not only is a function continuous, it's piecewise monotone. So it's piecewise constant or increasing or decreasing. You can also get CK. You cannot get analytic. Okay, so that's actually, which is a little bit annoying. You cannot actually get it down to prove that it's piecewise analytic.
You can, and analytics, no.
What?
C infinity,
No, you can't get C infinity. Yeah, you can get CK for every K. Now you might say, well, that's C infinity. But no. I'm saying it's almost everywhere CK. It's hit all the final many points at CK. But there might be infinite points things go wrong. All right, so I won't go through this, but it's a similar kind of computation. Similar kind of computation so that the function has to be monotone. I guess piecewise. It's not actually monotone because the functions you draw in calculus, they're not monotone, but they're piecewise monotone. And that's true in the O-minimal structure of the elements.
Do you have a concrete example of the function which is CK for all k?
Yeah, that's, okay, so not really, it's what the examples come from quasi-analytic classes. So you have these classes of functions which satisfy with identity principle, but not identity, it's not the principle that the Taylor series expansion determines the functions. You have some kind of summation method other than usual summation method, which determines the class. And you can show that for these classes, you join them in an appropriate way. So the reals using a linear structure, and you can build functions out of those that are.
Will not have really these like polynomial functions. Just be higher and higher degree.
That's definable for Lamas. Okay, so this maybe not the something else that but these ones with quadratic class. There's a theory behind it. This is supposed to just construction. Of course, I don't know of any examples which come from functions that satisfy nice equations, but when I say differential equations. Yeah. Okay, so let me show you how cell function works. We have the continuity. And this is we have 2 slides. Okay, so we're going to work by induction on in. We're going to show that you have these definable sets in space. You can cell decompose so that they look like you break up into cells. So, and along the way, to actually get this to work, you also need to prove by induction that you can make have a function which defines in variables if piecewise invariant. So it's continuous in the sense. Case of n equals 1. For the cell decomposition, that's the definition of O-minimality. O-minimality says that take any definable set of weights and points and intervals. You can find how many of them, or you can take points and intervals and just like intersect them and define it. You get a cell decomposition which works for those finally definable sets. That's the definition of O-minimality. And the continuity condition, well, that's on. So now you go to n plus 1. And you have a bunch of these definable sets. Let's just see if we can just think about one for now. 1 definable sets, and that quite enough to draw. There, we can draw. So you have our 1 definable set. It looks like whatever. Okay. And what you'd like to do is you'd like to just project down to 1 dimension lower, and maybe make this slightly more custom. Project it down to 1 dimension lower, and you look at all of the sets you get when you project. There's the all this stuff here. And say, great, these guys projections definable. I can cell decompose this. And you do. So you've got points, you have this interval, it's the point, that interval. And then over each of these points, the boundary of the sets above is finite. And this is where strong linearity comes into it. Strong linearity, another way you could say it is that those boundaries are uniformly finite. So if you have a family of definable sets in one variable, the number of boundary points is boundary. That's really what's on the analysis. So you can look at all of the boundary points here. So here we have first boundary point there, this one there. And you can look at the function which picks out the boundary point, the first boundary point. This guy there. Look at the function which picks out second boundary point, which is this one here. And okay, this one has a third boundary point and a fourth boundary point. Okay. Those are all definable functions, and hence by induction, continuous after you self-compose. And really, just to describe the set, I just need to know where the boundary points are and what lies in between. Okay. And that's basically it. Okay, so the cells that you get are going to be, some of those are going to be the continuous functions over cells of the boundary functions. And then some of the spaces. That's it. And then to prove the continuity theorem, at least in the case of the reals, it's just like what I just it's like the real analysis argument we did. Which you do it in the variables. Okay, so wait, move that backwards. All right, so let me just say that's that was arguments for the reals. Gillet, Steinhorn, and Knight showed that actually it's you don't need to assume the references. You don't even need to assume, in fact, you don't even need to assume that the ordering is dense. So they have a series of 3 papers. These are also very nice to read, although the proof, the monotonicity and continuity theorem that I did earlier, that was basic, very basic real analysis. Okay? Just the kind of exercise that you give the student the proof week using the continuities. The proof of the continuity monotonicity theorem, if you're doing it for a general O-minimal structure, where you don't assume you're dealing with the reals, well, it's elementary, but it's a big. It's it literally I think that argument works, but it comes back to what I was saying about the O-minimality policy, that either it's beautiful or it's a horrible disaster. And if you're in an O-minimal structure which is not the real numbers, horrible disaster can be really horrible. Okay, so the total absolute disaster as to what these what the sets are like. And you keep pushing to some point you say, yeah, but it's also O-minimal is beautiful. So it can't be that ugly, and eventually it collapses. So all of the disaster collapses, and you get that the functions are continuous, or monotone, differential, whatever it is. And so this is the second paper, which is probably the most important from the point of view of what we're doing here, where they show that if you just assume your structure is O-minimal, so it's an ordered set where the definable.
Thomas, I'm a bit confused. So O-minimal originally was written with a small O. Then there appeared a script capital O, and now it is zero minimal structure. Is it the same?
I'm sorry, it's not my fault. And actually, originally, like I said, if you go back to that Scanlon paper, he doesn't even call it O-minimal. He calls it finite type. Right? So and then you're right, and then in their paper they do it with scripto, and now they do it with Enduro, and then they're even the last one. Both of them are small.
So only the conversions.
Yeah, it's converting. It's a conversion to what we.
How is that? Yeah, I was told that the O is for order.
It does.
Where did they get zero?
It might be. If you ever look at what Alan writes, it's sometimes it doesn't always match with ideas. Because the symbols used don't always correspond to what he meant. And we got probably yes, it means work. So what does the O-minimal mean? It comes out of it's inspired by ideas in logic and stability theory about strong minimality and minimality structures. Where structure strongly minimal means that structure minimal means that every definable subset are defined as cofinite. So it's kind of like O-minimal. You can only define it using 12. And O-minimal is supposed to be just those sets that you find using this big work. So it's the minimal thing you can possibly have in given work. The point of these papers, I'm not going to go through the proofs, is that you can axiotize what you mean by O-minimality without assuming you're working with real numbers. And maybe you only care about the real numbers, and that's usable. The real numbers are important structure. But to analyze even the nominal structure of the real numbers, sometimes you pass to some associated series model, or you might not want to have to worry about, oh, is the whole theory O-minimal or something. And what they prove is you don't have to worry about it. Okay, so if the structure itself is O-minimal, not worrying about what happens with the bounds, then automatically you get solved in opposition. From which it follows that automatically it's strong number. You really do get these uniform bounds always, just as an automatic consequence of having O-minimal with the structure. They also worry about the case what happens to structures and isn't dense. And you might think, well, okay, is that interesting? And the answer is no. So that's basically, they've done all the work for you to do about that. Okay, so it's yeah, there are ordered structures that are discrete, which satisfy the O-minimality condition, but therefore there's nothing interesting. So I think that might be the points. Wrong way, right? Yeah, I think that might be the points where I'll end for today. And next time then I'll talk about some of the basic work. Any questions?
Thomas, may try to summarize your today's 1 hour of talk in just 2 phrases.
Sure.
So we have a theory of algebraic structures like rings, and then we have the tameness condition, meaning that we deal with finite number of ring operations, which brings us to polynomial and rational functions. And this is a very tame class of functions. Now, if you extend the setting to the real closed fields, then we add the operation, the order, and then the algebraic tameness is reduced to definability, but still different structures may behave differently. Some of them may be tame, some of them would be wild. So the O-minimality is the weakest condition of tameness that can be imposed on the real closed fields to guarantee that it's well, whatever you have defined in this field will be say tame, like finite beta numbers for this finite cell decomposition and so on.
Yeah, I think that's
so the only different problem is that in the algebraic context, you can easily check the algebraic tameness.
yeah. So the algebraic by algebraic context, you mean field operations on reals. You know,
just fields.
Well, just fields, but even fields. Fields, I don't think of as tame. Like the rational numbers are not tame. So if you're only considering you can be asking questions like, are there solutions to the system of equations? We don't know whether you can do that. Whether there's a procedure for answering that question for the rational numbers. That's an open problem. Whether that's decidable. It's certainly not decidable, more complicated kinds of first order conditions you might ask about the rational numbers. Julia Robinson proved in 1949 that the theory is not decidable. So the algebra itself, once you start asking more complicated, adding more complicated questions, can become untamed, wild in general. But for some structures, the reals, the field structure, and we'll talk about another kind of operations might be on that, still have the states of the operation. So they're defined as finite numbers.
Question maybe right for this one, but just a little bit more naive. So here that not every nominal structure in the algebraic structure is number of possibilities.
Yeah, so it's not clear, but it's true. Okay, so it's something that's that I'll be explaining. I'm not going to get proofs, but I'll explain that there are O-minimal structures that go well beyond that. So for instance, the answer to Tarski's problem, we don't know about its decidability, but we do know O-minimality. We take the reals, the addition, multiplication, and the exponential function in ordering. That's a good.
Yeah, but maybe you can. I mean, certainly maybe you put into some transference real cost.
It's they define now it's not the structure is not equivalent to the structure on.
Yeah, that goes my question.
Yeah, it's not equivalent to the structure of something else. That makes sense.
meeting in Dignity 11:30. I should say just ahead that Gareth Jones is the one next to the last talk today. Who had to cancel unfortunately, and he last nicely agreed to give the talk. Everything will post the file later. So the talk before last in STEM down.
What foundations? I agree with that. I think it's quite like that. It's not a fire freedom. Projected results. So usually formulas, but I didn't involve in Sure, the way that you present that's not here's the story, but maybe another way you can change the like on sets like the same just structure right. Yes, like you also make the examples where it's challenging. Yeah. Because our ex enemy, I might think that things like very real and it might be function on the side. Why it's useful sometimes. Add exponents without define